But before going on to 20, do you have any questions about this? Are you going to finish? You know it's okay.
By reviewing literature, we have seen that Professor Angus in North Carolina University has taken into account the effect of aging and have a relationship with the VS. Have you considered this kind of effect in your research?
Yes, I have considered that effect. If I have evidence that that soil is old and it has not liquefied before, I think that method that he has, I think it's Andros, and I forget the last person's name, the more recent one, I think that idea of using shear wave velocity that you measure in the cemented aged soil versus what you would get if it was a late Holocene material, using that as an aging factor to increase the cyclic resistance ratio, I think that's a good method. Just be careful that that soil has not liquefied. And I think the shear wave velocity contrast gives you an index of that. But I like to do aging. I like to look at this from different angles. And I always like to get the geologists involved to make sure that I don't mischaracterize the age of these deposits. But I have used that, yes. I think it's a nice piece of work.
With regards to the figuring method with the shear wave velocity, I'm wondering what are your thoughts? Because what I found from my practice and my experience is that usually it doesn't, like the results do not agree with the evaluations that we sometimes do with the SPT and CPT. And now I'm working on a project where the SPT and the CPT agrees, even though we have measured the energy for the SPT, but we know where it's around and it's agreeing very well with the cone. But with the DS, I found out that liquefaction is going to trigger, but the thickness of the deposit that is going to trigger is like around 1.5 meters less thick. So that makes me wonder if I may be correcting too much for the aging, or it's related with the limitations of the method. Or...
Professor Kramer is going to talk about it, but my opinion is the CPT, you may have guessed this by now, is the preferred technique. SPT is a distant second. Down there, way below, is shear wave velocity, and I believe it's a small strain property. It measures small strain properties, not large strain, and it doesn't. Relative density is the most important thing. Ramon Verdugo did a really nice job in a conference just a few years ago about arguing about the fact if relative density is so important, shear wave velocity is not as sensitive to relative density as CPT resistance is. So there are many reasons why the CPT is preferred over the shear wave velocity. You should always measure shear wave velocity because you need to do a site response. And I think it tells you very low shear wave velocities, very high shear wave velocities, it tells you a little bit. But I think as Professor Kramer will show you, there's a lot of uncertainty with the VS correlation. And I think people are working on it, but I just think fundamentally it will never be as good as the cone.
Is it acceptable to combine perhaps a cyclic resistance from one of these methods with a CSR from a computational simulation?
Strictly speaking, the Boulanger and Idris methods say you need to calculate CSR our way, because that's the way we did it. Ray Seed and Rob Moss say, oh no, you can do that. You can do the calculation your way because we based our correlation on this R sub D that we developed based on a 2000 ground motion analysis. Peter Robertson, I think, is silent on that issue. I have been in situations where you go to greater depths. There was a project in New York with a silty soil at great depth where that's one reason why I did it with the Moss et al. Method, is to take advantage of their R sub D, and at the greater depths gave it a little bit more weight for the R sub D. But I don't like the K sigma of the Mossad method. I skipped over that, but he basically says K sigma is 1 because in the database he looked at, he didn't have enough magnitudes to see it, and he didn't force it to be in there. Whereas Idris and Boulanger go, there's got to be a magnitude scaling factor. It's there, and then they use the data to calibrate it or regress upon it. So no one's perfect, and that's why you want a combination of methods. And you're going to earn your money as a geotechnical earthquake engineer when you're outside of where the data is, and that's at greater depths where these things make a bigger difference. And the thing that's going to help you is the critical state framework. Okay, let's move on and see if I can get some more questions talking about liquefaction of fine-grained soils and gravels. Whether you want to call it liquefaction, cyclic mobility with limited strain potential, cyclic softening, cyclic failure, bad things can happen in fine-grained soils due to earthquake shaking because of the increase in pore pressure and the reduction in effective stress, which causes a softening and a reduction in strength. The best example of this, what drove me into this research area, was the Khojaly earthquake. I already mentioned that this is like the Leaning Tower of Pisa, dynamic version. There's only 1.5 meters of low plasticity silts underneath this building and about 5 meters of dense gravel. Can silts liquefy? Whatever you want to call it, they cause a problem when that building tips over. It looks like liquefaction. This looks like liquefaction ejecta. This is also a silty soil site. This doesn't show as much ejecta, but you see the ground heaving and the building punching. This shows a floating slab literally becoming a floating slab at another silty soil site. So these silty soils, slightly plastic silty soils, and sandy silty sands liquefied in Adapazari. Not just Adapazari, but also in the Chichi earthquake in Taiwan. And Jonathan Stewart did some nice work on that. Went back to look at the Northridge earthquake at Ventura Valley, and it liquefied there. Adapazari, for the Turks in the room, is Island Market. A bridge that the Romans built across this river 1,500 years ago is now several kilometers west of the current alignment of the river. So it's clear that this river was meandering all through here, and this active fluvial environment. Talking with people who lived in this city for many years, they said up until the time that dams were built upstream of these rivers, they would flood every other year or so. And they would get these overbank deposits and have to walk through the flooded water, and the silts would then basically be built with that deposition. What's interesting is when you look at damage statistics and the cold colors like blue or low percentage of buildings being damaged, and the hot colors, especially red, or high percentage of buildings being damaged, is you see the typical things that more buildings are damaged on soil than on rock. Ground shaking is one issue, but the other issue is liquefaction. What's also interesting is there's areas with intermediate levels of damage adjacent to areas that had high levels of damage. So we decided to do surveys on lines through here, also go and pick up case histories of particular buildings that were interesting off these lines so that we could collect this data before it was erased. Now that we have the data before it's been erased, we can then go to the next summer and do CPT with borings and look at all the soils in Adapazari, and they're generally of 4 types. There's slightly plastic, low plasticity, silty soils on top of some sandier materials that can liquefy. There's silty soils on top of dense soils that will not liquefy. There's clayey materials over some silty and sandy soils that may liquefy. And then there's high plasticity clays that will not liquefy on top of dense, clean sands that will not liquefy. If we look at one survey of 60 buildings, a small subset of the many hundred buildings surveyed, we didn't just survey the building damage, whether there was no building damage, architectural damage, cracking of structural members, permanent deformation against cross-structural members, partial collapse and collapse. We also looked at ground failure. No ground failure, minor amounts, maybe less than 100 millimeters of settlement, a little bit of tilt. 2-3 was more than 250 millimeters or 300 millimeters of settlement and more than 3 degrees of tilt. When we come along here, we see there's areas of significant ground failure, there's an area with no ground failure, and then there's areas with even a higher rate of ground failure. Now, badly built buildings, and there's some bad buildings in Turkey at that time, will have shaking-induced damage. But you can see that the damage of the buildings is much higher rate on top of the liquefiable soils. When we went back, since we collected this data in 1999 after the earthquake, we came back the next summer, and then we took those soil profiles and put them here. This has some liquefiable soils at depth. This has non-liquefiable soils. This has liquefiable soils on top of liquefiable soils. That is, if you admit that low plasticity silts liquefy. This is one of the best examples of that. We call this the tale of three buildings. Built by the same contractor, they're built at the same time, same structural design. The only twist is they put a black roof on the middle one for some reason. So flying in a helicopter is the only way you knew that this building had a slight difference from the other two. Other than that, they're the same building. The only difference, when you look at depth, you don't really see a significant difference in the soils at depth. Maybe a little bit of dense sand here, but you've got this being the same. What's the difference is this is the edge of the overbank deposit where you have about a meter of liquefiable silts beneath these buildings, and you have none of that under this building. There was no ground failure here. This building was in operation. No one ever evacuated it. When we came down the following summer, this building was gone, and they were talking about demolishing this building. You can see the ejecta here that happened in this location. If you apply the Chinese criteria, which was the method that the experts said you should use as recommended in the Aldedal 2001, you got a layer of that silt that had a low liquid limit, less than 35%, had relatively high water contents, so that satisfies these two criteria. But when you actually took the soil and you did the hydrometer analysis, these soils had more than 15% passing 5 microns. So by the Chinese criteria, these soils will not liquefy. But they did. And then you recognize, why did Arthur Casagrande abandon using hydrometer analysis to tell the difference between clays and silts? Because it's not the size of the particle that matters, it's mineralogy. So he said, forget about size, let's use a plasticity-based chart and an A-line, and if we have a lot of montmorillonite, we're going to be maybe up near the U-line, way above the A-line. If we're going to have a lot of illite type materials, we may be along the A-line. If it's more kaolinite and less clay in it, it's going to be more below the A-line. And so let's use plasticity index, not the size of the particle, as an index of mineralogy, because mineralogy matters. If it just happens to be a glacially ground up quartz material that's really, really small particles, it's still quartz. It's not clay just because it's clay size. It's quartz. Do not use the Chinese criteria. Do not. Don't even listen to me. Listen to Professor Idris, who was one of the authors of the Chinese criteria. He stood up in 2004 and said, I regret Harry Seed and I ever publishing that, do not use it. When the person who is confident says, do not use a method that he had developed, don't use it. We could not bring the soils to Berkeley without disturbing them. That flight would have disturbed them. We brought Berkeley to Turkey. And this is a Berkeley cyclotriaxial device. I'm guaranteeing you it's in Turkey because it has President Ataturk. Every lab and every building in Turkey has Ataturk in it. He saved the country from being eliminated after World War I in the early 20s. First thing we realized, as we talked about, is we're mainly going to do cyclotriaxial tests because it's a cheaper, easier thing for us to bring to Turkey. And Mike Reamer would not let me have the cyclic simple shear device. But then we're going to bring some soils back, which we know are disturbed, but that hopefully are disturbed the same, and develop a relationship between the cyclotriaxial and the cyclic simple shear. And we found for these materials, C sub R was more like 0.7 to 0.8 because of the compressibility of the soils, the higher K naught, and maybe there's a little bit of OCR due to desiccation from the flooding. My National Science Foundation proposal was to show the world that soils that had a PI less than 4 were different than soils that had a PI from 4 to 8, which were different from soils that had a PI of 8 to 12, which were different from the PI. I believe that. I wrote that in my proposal. I had Rodolfo Sancio do 116 cyclotriaxial tests to prove how smart I was. I wasn't so smart. This is my best results in showing a slight difference that as the PI increases, there's a slightly more cycles to liquefaction. When I look at all the data, and what's the difference between 11, 13, and 15 cycles? And look at the shape of these curves. They all kind of look the same. When I looked at all the data, whether the PI was 7, 10, 4, I couldn't see a difference. Now some people say, well, it's because you had natural soil deposits, and there were parts in that soil that were low PI. Rodolfo took samples at the top, middle, and bottom of all of his triaxial specimens and did those Atterberg limits on each one of them to show that he had consistent ones. When he was inconsistent, he threw them out. Now, as the PI got high, we are now seeing clearly a clay-like behavior, and it's taking a lot of cycles to get to 3% single amplitude strain. But because those were natural soils, I shipped at great cost a big part of the soil back to Berkeley, and I hired another PhD student, Jennifer Donahue, to do cyclic simple shear testing, and for her, with water lithiation, to reconstitute specimens that had PIs of 2, 5, 7, 11, 14, and the baseline case was PI of 10. All the same material, but just by taking different fractions, you could mix it to get different PIs, slightly different mineralogies. If you look at the faint dotted black line below this, and then the color line, you see, okay, there's not much difference between PI 10, PI 11. But there also is not much difference between PI of 2 and PI of 10. In fact, PI of 2 looks more clay-like than PI of 10. And PI of 7 doesn't look that much different, maybe looks a little bit worse than PI of 10. But when you look at the details of this, you don't start seeing systematic differences until the PI is greater than 12, 14, 18, 20. Because of the controversy, I deliberately did testing extensively on PI equal 2 and PI equal 10. And if you look closely at this, actually a PI equal 10 is potentially a little bit more problematic. And the stress strain curves look the same. The cyclic resistance ratios are actually a little bit lower. So I would have a hard time saying those are different soils. Key thing that came out of this is the elimination of the Chinese criteria, primarily because size of particle doesn't matter. And that became the basis for the Bray and Sancio liquefaction susceptibility, where again, I like black, white, and gray. I don't like hard lines, but most of the soils under intense shaking that underwent cyclic softening or failure or cyclic mobility with limit strain potential were these soils that had high water contents with respect to the liquid limit. That's a good indicator of sensitivity. And they had PIs that were less than or equal to 12. Now what do you do when you have two groups of smart people that one says PI is less than 12, the other one says PI less than 7. I reviewed a project where people were doing PIs to a decimal, so they would get a PI of 6.8, it could liquefy. PI of 7.2, it won't liquefy. We have to step back and realize as we professors do these things to provide guidance, we're giving guidance. These are not laws. The soil does not obey us. Nothing magical happens between a PI of 6.9 and a PI of 7.0. There was actually a group of people that said, okay, Boulanger and Nitras are correct. They had two groups of samples, PIs less than 7, PIs from like 7 to 12. And they sent the PI less than 7 material to Mike Reamer to do laboratory testing so they could evaluate it. And Mike did all of his testing. And then they go, oh, no, we sent you the wrong batch. And so they tested both sets. And they looked exactly the same. If I can put a piece of paper of test results in front of you that show shear stress versus shear strain and show the development of the QP plot, if it looks the same, whether the PI is 4 or 8, why would you call it a different phenomenon? But the best way of breaking a tie between two smart groups is to go to the master. So if you don't want to do it my way, and you don't want to do it Nitras' way, then at least listen to Professor Kenji Ishihara, because when looking at a lot of tailings material, he found no difference when the PI was less than or equal to 10, and only saw that the CRR started to increase as the PI was greater than 10. I have no problem if you want to use PI less than or equal to 10. Of course, I prefer PI less than or equal to 12. And I do like this ratio as being a function of sensitivity. The primary controversy doesn't come because we have different opinions on soil mechanics. We have different definitions. Like most debates, there's semantics. Luckily, the work that they had done in 2006, which was repeated in their monograph, and the work that we had done in 2006 had discussions. And they published both of the closures that we wrote. And we basically found that the key was the definition. What Gray and Sansier are saying is if the low plasticity fine-grained soils have a similar response to sands that are dense, and you call dense sands liquefaction, I'm going to call it liquefaction. And so we call it cyclic mobility because we're thinking about it in terms of stress strain curves and mechanics. And Nitras and Ross Boulanger say you shouldn't be using a cone or an SPT especially to evaluate liquefaction of a fine-grained material. So they're going to go, I reserve the term liquefaction only for those soils that can be evaluated through penetration tests. And you should not be evaluating fine-grained soils with a penetration test. We have different definitions of liquefaction, but we both agree that you should actually do testing on these soils because you can retrieve undisturbed specimens. And you should test these, not only because you can test them, but because we have very little empirical data on these materials in the penetration-based liquefaction triggering procedures. So it's prudent to actually do your field investigation and your laboratory testing. One thing that pushed Professor Robertson off his ISFC of 2.6 is this one case history, where there are soils with low PI that had higher ISFCs that liquefy. So again, nothing is magical about 2.60. It generally is a good criteria, but you really should take plasticity index of specimens that have I sub C's in the 2.5 to 2.7 range to figure out what is the right value to use. And I've used I sub C cutoffs of 2.5, 2.55 sometimes. I've used an I sub C cutoff of 2.65. So in terms of cyclic mobility on fine-grained soils, based on this work that I've done with largely Rodolfo Sancio and Jennifer Donahue, which is based on over 150 cyclic triaxial and simple shear tests on both reconstituted and natural soil deposits, is don't use the Chinese criteria. Everyone agrees with that. Focus on soil mineralogy, not size. Everyone agrees on that, but we have difference of opinion on where the PI threshold should be. Just because the PI is 13 doesn't mean it might not undergo severe strength loss. Clays can undergo without strength loss. Use cyclic triaxial testing. Harry Seed left this in the dust because he had to go to clean sands and could not sample clean sands. So he had to use something like a penetration resistance. But we can sample these slightly plastic clayey silts or silty soils and test them. And all these things we know matter from our discussions that we had this morning. So my recommendation is the liquefaction triggering procedures have largely been developed for clean sands and non-plastic silty sands. So if you're going to apply them to a low plasticity silt, use considerable judgment. Be conservative if you have uncertainty. Better yet, perform testing on undisturbed specimens. And whatever the clay does, whatever you want to call it, it's what the clay does in terms of its shear stress versus shear strain and its QP plot that matters to you as an engineer. So you can avoid the controversy. You just focus on the resulting stress strain curve and the effects of whatever you want to call it, liquefaction of fine-grained soils. Now let's jump over sands to gravels. There are people that say gravels don't liquefy. False. They liquefied in the 1906 earthquake along the Russian River. They liquefied in the 1983 Bora Peak earthquake. They liquefied in the 1999 Gojali earthquake. And you can go to Les Harder and other people's theses to find even additional case histories. So the field has told us they've liquefied, especially if they have fines between the gravel pieces or they're encapsulated with a material that won't allow them to dissipate pore pressure. In general, uniform gravels have low ward ratios. For the water to carry a gravel downstream takes a lot of energy. So you're not often going to find natural gravels that aren't dense. So that's one reason why we don't often find these case histories. They tend to have high hydraulic conductivity, so even if they were going to be a little contracted, the water can move out of the way, and you can get some drainage occurring during cyclic loading, which would also mitigate the liquefaction phenomenon. So all of those things suggest that uniform gravels built by nature tend not to be an issue. Well-graded gravels tend to be a little less resistant because you've got the grains between the particles, you don't have as high hydraulic conductivity. In nature typically makes low void ratios, and hence they're more resistant. So native gravels are less likely to be loose, and hence you're less likely to have a liquefaction issue. But when we build gravels, sometimes we're not so smart, we drop them slowly through water to make a gravel fill that's basically a hydraulic gravel fill. Those can be loose, and therefore they can liquefy. But they're difficult to characterize because of these large particles. So one way of characterizing it is the instrumented Becker penetration device. I talked about that already. Another method that I'm not as keen about was used in being able to look at this case history where there was some gravel materials that appeared to undergo some ground deformation that was resulted from liquefaction. Gravel content was 25 to 65%. They were anywhere from being fairly uniform to being well graded. These investigators used the Chinese dynamic penetration test. This is a picture of this thing. It is non-standard. It's a dynamic test. It's like going back to the 1900s and using a not-so-standard penetration test. If you're going to use this Chinese dynamic penetration test, you better measure the energy, and you better hope that the geometry of your little solid specimen is exactly right, and you've done everything perfectly. I think just because the Chinese developed this and they have a little bit of data, we should not continue to use this method for the future. I think it's time to say, okay, but there's a lot of limitations. We don't want to go forward with this. Let's go another way. Because, for example, here's shear wave velocity. The low damage is the blue, and it has a hard time distinguishing. So that's one of the issues with shear wave velocity. But this penetration resistance says all of these sites liquefied, and by a fair margin. I haven't seen it been able to discriminate as well as it should. I like the cone. But you can't drive a cone in gravels. Yes, you can. 15 centimeter squared cone, with patience and persistence and luck, you can push the cone. This is the Wellington Harbor. It's one of the 4 major harbors in the country of Wellington, which is an island country, so ports are very important. It was heavily damaged, put out of commission for several months as a result of the 2016 magnitude 7.8 Kaikoura earthquake. You can see the damage to the piles, you can see the gravel liquefaction, you can see the deformation of the wharf. Because it was a magnitude 7.8 and it was at some distance away, about 60 kilometers, it had a relatively long shaking for a shallow crust earthquake, not a subduction zone earthquake, that even with a PGA of about 0.2, 0.25 could lead to liquefaction. Importantly, this site was shaken by some magnitude 6.6 earthquakes at about the same distance, and it did not liquefy. So this is a nice case history of shaking that did not liquefy these gravel fills, shaking that did liquefy. The nice thing is they had done a survey right after those earthquakes in 2014, and they then went back and resurveyed after the earthquake in 2016. So we have very good measurements of how this moved out. This was done with a UAV survey by a professional surveying company. We also had Michael Olson from Oregon State do LiDAR on the ground, and we had Michiko and I do the old-fashioned measuring things with a tape and measure. They were actually all pretty consistent. What happened is the ground liquefied. The wharfs are pile supported. They don't have strong, big bulkheads, so this is laterally unconfined. So things went down about 200 to 300 millimeters, and then at the edges, it went down and out. So if something moves laterally 200 millimeters, of course it's going to come down at least 200 millimeters, and then it's going to come down even further because of the 1D compression. This is just showing some, most of the lateral spreading was within about 100 to 200 meters of the face of the slope. The lateral spreading pushed the wharfs, which caused the cranes to be pushed out of operation. This is the grain size distribution using the number 4 sieve as the break point between gravel size and sand size. This is what we got from the ejecta. This was testing. I wasn't there initially, so this is actually Mishko Chubanowski and his students collected samples and did grain size distribution. In the background, in the gray, you can see grain size distribution done on drilling that they had done in this material before the earthquake, and it's consistent. So looks like the material that was dumped here It has the same grain size distribution as the material that they drilled out before the earthquake. So therefore, we believe the ejecta is the material that we think it is, and it has 30 to 70% gravel. But that means it has 70% to 30% sand and maybe slightly silt-sized particles. So if it has 70% sand, it's a sand. If it has 30% sand and 70% gravel, that's kind of at the point where it's transitioning from a gravel to a sand. So most of these gravel fills are actually not, they're classified as sandy gravels, but mechanistically, they are sands that have large gravel pieces floating in them. They said, you're silly, professor. We have tried cone, it hasn't worked. Even SPT has been a problem. So we made a solid penetration device, and we drove it into the ground. I go, well, do you have any energy? No. So they have penetration resistances by a non-standard technique with no measurement of energy, and they're just going to engineer the retrofit of this wharf based on that. I said, you know what? I will pay for the truck that I work with in Christchurch to come all the way up to the north part of the South Island, take the ferry to the South Island of Wellington, Northern Island of Wellington, and do this testing. And I'll get Michigan to pay for some of it. I'll get the National Science Foundation to pay for some of it. I think I even got Peer to pay for some of it. And then eventually I got money from them because they realized I could push a cone using the same pre-collaring system that we had developed in Christchurch for the gravels there. Just reminding you that a pre-collaring system can punch through the dense gravels and then continue to get good data. We did 47 cones initially. We cased through the fill, because we don't care about the fill, it's above the water table. We used a 15 centimeter squared cone with this rig device, with the pre-collaring system, and out of those 47 cones, only 13 hit refusal, typically by too much inclination, before 10 meters. Those 13 times, we moved over 1.5 meters through the dice, and we got down below 10 meters. Since then, we've done about 120 cones and gotten them all down below 10 meters and gotten incredible information. So now the port and the consultants working for the port are not using their non-standard solid cone with no energy, and solid SPT procedure with no energy measurement. They've thrown all that data away, and they're only using the cone data to make their site investigation. The great thing about the cone, as you can see here, is you get the penetration profile. You get the sense of seeing, okay, the gravel fill is 20 meters thick on top of a silty soil, on top of the dense, it's called, I'm forgetting the name of it, Wellington gravel, I believe. And then you have the fill on top of about 10 meters of the gravelly fill. It was end dumped into this material on top of the silt. So the profiling effects that you get from CPT is invaluable. In the gravel fill, the QCs from 25 percentile to 75 percentile are in a pretty tight range, so we know it's relatively loose. And the I sub Cs are telling us it's not a gravel. If it was gravel-like behavior, the I sub C would be less than 1.3. The I sub C is actually more in like a sand to silty sand mixture of 1.9 to 2.3. Now there are spikes that you see occasionally. That's us hitting a big gravel piece. I could filter that out, but then that would almost be a self-fulfilling prophecy, so I kept that in there. Because even doing the analysis with those spurious spikes in there, I get essentially the same answer I would get removing the spikes. That this soil is going to liquefy for a magnitude 7.8 earthquake with a peak ground acceleration of around 0.25 G. So this gravel fill is actually a sandy fill with a lot of big gravel pieces in it. It's controlled by the sand-silt mixture. This is just showing some more detail, and you can look at these slides. You can also look at the paper that I included. But you're seeing that the CSR is in red, and it clearly causes liquefaction. If I have uncertainty on that, it can move around a little bit, but we clearly have liquefaction predicted. And if we ignore the spikes, we have enough material below that, which has CRR less than the CSR. We expect large, significant settlements. We got large settlements. We're seeing a behavior that's consistent from the sand-based, CPT-based procedures when applied to this sandy material that has a bunch of gravel in it. So even with 30 to 70% gravel-sized particles, the CPT could characterize them. They were characterized as being thick, unconfined, and loose. They had relatively low tip resistances. We knew they had a weak fabric because they were fluviation through water. We knew they were young because this port is an extension of an existing port that was done in the 70s, so at the most 50 years old. And the cone told us by ice of C that they were controlled by the sand mixture despite having 30 to 70% gravel size. They had a low liquefaction resistance and a high deformation potential, and that's entirely consistent with what these conventional sand-based methods are. So I think you can take these sand-based methods with proper judgment and move them into the low plasticity silt and silt range. Because again, soils don't know the 200 silt was invented. A coarse silt doesn't know it's that different than a very, 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 very fine sand. Same thing. A coarse sand doesn't know it's that different than a fine gravel. And so we can extend these methods out with judgment. Questions? English or Spanish?
Buenas tardes. Tengo dos preguntas. La primera pregunta está relacionada con el tema anterior. Respecto a las gráficas de relación de esfuerzo cíclico versus resistencia, las curvas que me definen el umbral entre licuable y no licuable. La pregunta es si es posible presentarlas en función de la deformación cortante o la deformación volumétrica. Tal como lo hizo Osi hace muchos años en unos trabajos en donde presentan las curvas en función de la deformación cortante.
That's a very good point. I don't need to hear myself in Spanish. That's a very good point. And I'm going to show you a plot, and I normally look at a plot in terms of cyclic stress ratio versus QC1N clean sand, with not just looking at the cyclic resistance curve, but looking at shear strain in the background. Because I don't just care about triggering, I care about effects. And so seeing how you get close to the CRR line can still lead to some shear strain or some volumetric strain, and how you cross that line in some cases can lead to very large shear strains, in other cases can lead to just a slight increase in shear strain. That's very informative. So I think that's a prudent and wise thing to do. I agree.
La segunda pregunta es respecto a la evaluación de la licuación en función del índice de plasticidad. Pues, viendo las presentaciones, se trabajan con rangos de plasticidad demasiado bajos, menores del 10%. Mi experiencia me ha dicho medir la plasticidad de suelos con métodos clásicos de cazuela es bastante impreciso. Además que tiene afectaciones de la forma como se hace el ensayo, si se seca previamente al horno o si se hace en condiciones de humedad natural. La pregunta es, ¿cómo deberíamos medir esos parámetros para que sean confiables?
We used the standard U.S. practice of rolling the soil on a plate to get the plastic limit and the Casa Grande cup to get the liquid limit because we were trying to eliminate the Chinese criteria, which was initially based on that, or at least used in the U.S. based on that. There are different ways of getting the plastic limit and liquid limit, but we chose to do it that way to be consistent with and change practice. When we first had a very good lab do it, we ended up with a lot of soils that had no plasticity index, even though the liquid limit was higher. And so we kept some of that soil, and we had Rodolfo Sancio, who's one of the most careful experimentalists I've ever met. He's a great field engineer too. He worked for 4 years for his father, who had a PhD in geotechnical engineering, and his mother's an engineering geologist, before he came to Berkeley. So I'd like to take credit for him because he was my PhD student, but the reality is he was brilliant and experienced and probably more dedicated than I am on every little detail. He reran those tests and found out that when the liquid limit was 33 or 35 or 37, there actually was a plastic limit, and the PI was not 0 like the lab said. So that shows that test is very dependent on the operator. The British method of doing the falling cone is less dependent on the operator, but we have much less data in that in the US, and so you kind of have to work where you have the data. We need to come up with a better method for doing liquid limit and plastic limit to allow us to move forward. I think those methods were developed in the early 1900s. It's been 100 years. So right now, I would say researchers should try to develop a better method. But in the meantime, I still do the plastic limit and liquid limit the way we did it in Turkey, the way I did it before Turkey and after Turkey. And I have looked at comparisons between Falling Cone and Casa Grande Cup, but I just make sure whoever does the testing is as dedicated as Rodolfo Sancio. I don't know of a better solution than just making sure the person who does that testing knows how important it is to be careful and try to get as reliable results as possible. And then realize plasticity index is an index of mineralogy. I have never reported liquid limit or plastic limit to a decimal point. It's 12, or it's, liquid limit is 35. It's not 34.8. And even with that, I realize there's shades of gray. There's a dam in the US where they use the Martin criteria that says, actually the falling cone was used for the Chinese criteria, we should actually bring it down. So they were saying, okay, if the liquid limit is less than 32, it would liquefy. If the liquid limit by the Casa Grande Cup is above 32, it won't. They did a bunch of tests, and when the liquid limit was less than 32, they did remediation under this dam. When the liquid limit was above 32, they did no remediation. Knowing the uncertainty in that test, why would you do that? So be careful and realize these are indices. I don't believe anything is black and white.
Una pregunta con respecto al tema de los procedimientos de evaluación digamos, de licuación. En los procedimientos, digamos, simplificados que muestran, pues los muestran con base en pruebas in situ, pero no he visto o no sé si exista procedimientos relativamente simplificados también evaluados con parámetros de resistencia al corte, con parámetros efectivos, por ejemplo, pues el ángulo de fricción en el caso de las arenas.
I don't understand what you mean by deflection angle.
Friction.
Fricción.
Friction. The state parameter is the most important thing, and we hope that penetration resistance is capturing the importance of the state parameter. The state parameter is connected to the peak friction angle, but I don't think you have to go there. I think it's more direct to just use the penetration resistance as correlated to the case histories on whether liquefaction was observed or not observed as the primary method. I don't know, Steve, do you want to talk about that?
I would just add that while we complain about or we criticize the shear wave velocity measurement for being at a different strain range than the range of strains at which pore pressures reach very high values, friction angles correspond, they're mobilized at strain levels that are much greater than the strain levels at which liquefaction typically occurs. So I think the friction angle has a greater influence on the effects of liquefaction when we start seeing large deformations than it does on the generation of pore pressure. So the pore pressure problem, the initiation of liquefaction that we've been talking about, is much more closely related to the volume change characteristics and how that tendency for contraction or dilation is going to cause those pore pressures to increase. Then, if we start developing large strains, either cyclically or in a static monotonic manner, we'll see that the friction angle becomes more important at that point.
Yes.
In the plot showing the cyclic stress ratio versus tip resistance, there's quite a few data points that did not liquefy that fall into the liquefiable zone. To what extent do you attribute that result and how can we assess that? Take that into account when doing an assessment of the liquefaction rotation?
It is a simplified method, and there are a number of other factors. We deliberately set the bias to be conservative. We're more nervous about closed circles or liquefaction case histories being on the right side of that curve than the open circles being on the left. But I think there's some work to do on that. In fact, one of the people who's done a lot of work on that is Professor Kramer, so why don't you answer that?
Well, there are a lot of uncertainties in the various case histories and their interpretation. And we don't know necessarily the ground motions at these case histories. There are very few case histories where ground motions have actually been measured. So we have perhaps nearby ground motions from which we can estimate the peak acceleration for determining the cyclic stress ratio to correspond to that case history. Sometimes we have to use ground motion models, and those ground motion models have a lot of variability in them as well. There's uncertainties in penetration resistance, spatial variability, the operator error perhaps, particularly in standard penetration test results. And so it's not a distinct boundary when we look at the case histories. This uncertainty leads to uncertainty in the cyclic resistance ratio. And that's one of the reasons we go towards the use of probabilistic analyses and interpretations of these things. And so for the curves that you typically see plotted are deterministic curves, and they're chosen to be conservative. And they generally prove to correspond to probabilities of liquefaction, maybe 15% or so. But a more complete analysis and the kind of analyses that the profession is going to be moving towards in the future are going to account for that uncertainty more explicitly. And there's ways to do it that don't require detailed probabilistic analyses on the part of the engineer. It should be built in and can be built into the procedure so that you can do a conventional analysis, but using a ground motion parameter, peak acceleration, or combination of peak acceleration and magnitude that are selected to give you a desired and user-selected probability.
Yeah, I think now's a good time for a break, and we will start back up in 22 minutes.